Welcome to our next tutorial in our series of tutorials on how to use machine learning tools and machine learning methods. My name is Vlad Kindratenko. I will be giving a presentation today, our tutorial about natural language processing with PyTorch. So we had a tutorial on PyTorch, and the examples that we use for the tutorial were mostly about image processing or image classification tasks. And so I thought that there is actually a lot of work that is also happening with processing something else as an image, such as audio files or text. And I thought that actually may be good to have a tutorial that will introduce specifically the NLP with PyTorch. And so that's the origins of this tutorial. The tutorials that I will be presenting actually is not running on HAL. I'm running it on Microsoft Cloud, and this is actually a series of the notebooks that Microsoft provides in their PyTorch fundamentals training series. So you're welcome to follow this notebooks. I posted here. I just dropped a link into the chat so you can see where this notebook is coming from. But okay, let's get started. So our objective is to basically to learn how to process natural language in a way that we can extract some knowledge from it. And so we will look at what models work for this, what kind of problems we can solve with this, and how all this can be done in PyTorch. So, and again, this is the link to the notebook that I'm using. So you can connect to this notebook and also follow it from there. This notebook has several sections, and so we will start with a section that talks about the following. So what is the purpose of natural language processing tasks? And the simplest process you can think of is the text classification. So given some text, we can look at it and decide, for example, if this is an email spam or what category this text belongs to. So that's one possible application where we may want to apply natural language processing. We can also try to analyze what is the specific purpose of this text and what is the intent in that text. And so there is a different category called intent classification of tasks that NLP is good at. We sometimes also want to be able to understand the degree of negativity or positivity in the text. And this is referred to sentiment analysis. And so NLP is good at answering this sort of questions. Now, between the intent and sentiment analysis, this actually is the sort of the basic building blocks of conversational AI. You would imagine that the conversational AI would need to be able to judge from somebody's text if this is a positive sentiment or negative sentiment or neutral sentiment, and what is the purpose of a given phrase. So, these are very basic building blocks that are used by much more complex tasks. Now, another popular purpose of using NLP is to perform what's referred to as named entity recognition. Basically, extracting some entities from the text that have some meaning for some purposes. So, for example, finding people names or finding addresses or finding some medical terminology that is written in the task. A similar task is the keyword extraction, where we look for specific words in the text and try to identify, what else comes with them, so that we can find some of the meanings. And of course, there are much more complex, more interesting problems that are answered with NLP, such as text summarization. Basically, given an article, scientific article, you want to get a very brief summary of it, and so there are models out there that actually can do this. And of course, something like question and answer models, where you expect the AI model to actually maintain somewhat intelligent conversation with the user. So these are different tasks that NLP can be used to solve. And so what we are going to look today is how we get started with these tasks. In particular, how we will represent text in a way that it can be used by a neural network, obviously for the neural network, everything has to look like numbers. So how do we convert text like this into numbers? That's the first task. And also what sort of basic rudimentary tasks we can have with this representation and how we can improve this. So we'll try to go through some examples, through some networks that can accomplish this. As a reminder, again, this notebook is part of the Microsoft's PyTorch Fundamentals notebook that has Intro to Natural Language Processing notebook. So, so the first question is, how do we represent text as numbers? For anybody who has studied anything related to computer science, that basically alphabetical characters and numbers and other things that we want to represent, they are represented with ASCII table, or more recently use UTF-8 encoding. This encoding, that is an example of ASCII table encoding. Basically, each character in the alphabet and each special character, each digit is represented as an 8-bit number. And that representation is sufficient for the computer to basically to reproduce the actual representation of that number. So of course the computer doesn't know what the meaning is. So if this is a character H, that bit pattern, this bit pattern only has meaning for us as a character H, but from the computer's standpoint, it's just a bunch of bits. What they represent, who knows and who cares. So however, if you want to build a neural network that is able to work with text, you need to come up with some representation in which there will be some meaning given to this individual characters in some way. And there are basically two approaches in which text can be represented. We can represent text at the character level. Essentially, every character will be given a number. So ASCII representation is kind of that level, right? In ASCII representation, we give a number to each character, and so that's the character level representation. Now, perhaps just giving an ASCII value to each character is not necessarily the best way to represent from the point of view of natural language processing applications. So frequently enough, we actually use something like a one-hot encoding where essentially the entire dictionary of possible characters will tell us how long the representation vector should be. And then for each element in that dictionary, we will set only one bit to be high and all the other bits to be low. So of course, for something like 27 character alphabet, we will need to have a vector of 27 bits, and only one bit will be set high to every single character. Of course, a bunch of characters by themselves, they don't mean much. They don't really carry a meaning unless we group them into words. And therefore, the next level of representation is a word level representation, in which we basically create a vocabulary of all of the words available in the given text, and then we give a number to each word from that vocabulary. And now this approach is somewhat better because now we are looking at the groups of characters and that is words, and we are giving them some meaning. And we are treating them as entities, as unique entities. So there is a difference between one word and another word. So there is some meaning. Okay, so we will look at this word level representation, and we will start with this as our starting approach. So before we can get started with this, there is actually a whole bunch of what's going on here? There is actually a whole bunch of prereqs that need to be installed to run. In particular, the main prereq here is for this notebook to work is the PyTorch version 1.8.1, and then some of the utilities that come with it. So I already installed it, but if you are following this notebook, it is going to take a little bit of time to get this installed. And for those who have just joined it, I'm posting again the link to this notebook in the chat. All right, so let's take a look at the text classification task. So the overall idea is that if you are given some text, we want to figure out not necessarily what this text is about, but at least what category it belongs to. And so for that, we are going to use this data set, a GNews data set, and it consists of news headlines. And these news headlines are classified into one of these four categories. So it's either world news, sports news, business news, or sci-tech news. This data set is already built into Torch text, so modular, so it's easy enough to use. all we have to do is to, after we import Torch text, all we have to do is just to load this particular data set, so AG news. And so we are going to drop it into some folder. And the classes that everything is classified in this data set are just this: world, sport, business, science, tech. Again, so it is going to take a little bit of time to download this data set. This data set needs to be fetched from somewhere. But we will see that we are basically fetching two text files. One of them is a training data set and another one is testing data set. So there is a much larger training data set and there is a little bit in the testing data set. What this method returns is iterators. So Torch text data set will give us the train data set and the test data set as two iterators. And we basically can just go and ask what's next. And so here's an example. So basically what we are getting here is that there is some sentence, there is some headline, and this headline is classified into some category. And if you rerun it again, you will get the next headline and classified into some category. And this category will be one of these four categories here. So we can try to print some number of these categories. So for example, we can just go and print the first 10. Actually, yeah, the first few examples from this category, from this data set, from training data set, and we will see that this is the text and this is the category. Except that for whatever reasons, it's actually not printing the right category. So we would map the first index that is given into the class, and that class is always sci-tech for whatever reasons. It's not the right category. So I don't know what it is with this example. Occasionally it produces correct results, but most frequently it just actually doesn't print it right. But anyway, so the point here is that there is text, and for each of the category, for each of these passages, for each of these sentences, there is a classification, manual classification into which category it belongs to. All right, of course, yeah, some detail, because it's iterators and we want to have, we want to reuse them many times, we need to convert them to lists. So this code will basically convert those two iterators to lists so we can use them now. So the very first task for us is to convert this text into numbers, because we need this numerical representation so that can be used to build some tensors that can be inputs into our network. So we're going to use word level representation, and in order to do so, we first of all have to extract words, and so this process is called tokenization or tokenizing. So we need to go and extract each individual word from the text and actually strip these words from many special characters and so on. And then once we have all these individual words, we can actually use those words to build a vocabulary of all these individual words. And based on that vocabulary, we can generate a numerical representation. We can say that, you know, this word will give it an index 0, and this word will get an index 1, and this word will get an index 2, and so on. That vocabulary. And so this way we have very quick, immediate conversion of words into numbers. Let's actually do this. So first of all, we are going to use this tokenizer, which is basic English tokenizer. So this is again the utility in PyTorch text that will know, you know, what are the words in English and what are the rules of how words are formatted in English and how to strip of this additional characters. And so suppose now I can actually run this text again, the tokenizer, and I'm going to get just this sequence of individual words. So these are individual tokens or words that were extracted from this sentence. And so we can take, for example, any text and run it through this tokenizer, and you will get just a collection of individual words, a list of individual words which are ready for us to consume. So let's actually take the entire training data set, and turn it into a dictionary. So for that, we need basically a dictionary. And in that dictionary, we are going to essentially assign a numerical value to each of the words in the dictionary. So first of all, we need to extract the words. And so for that, we will simply go through the entire data set, training data set, we will take individual line from the data set, we will pass it through the tokenizer to get the individual tokens, and then we will have this method called counter update. And this counter update method actually does two things. It finds the word in the dictionary and then increments and so adds that word to the dictionary. If the word is not in the dictionary, it creates a new record for that word. So at the end of the day, we will end up having the entire dictionary of all of the words. And then we can build the vocabulary again using this method from torch text. So that takes a little bit of time because we have to go through the entire data set, but that's done. So after this, we basically have the dictionary of all of the words which appear in the training data set. So with this dictionary, we now can, for example, take some text, any text, hopefully consistent of all of the words that are in the dictionary, because if there are words which are not in the dictionaries, then this is not going to work. But if you take any text that includes words from the dictionary, we basically can encode each of these words into a numerical representation of that word in that dictionary, or the numerical index. So with that, we will write this simple function called encode. This function takes the text, input text. So for example, this will be our input. It will tokenize it. And for each of the tokens, it is going to just convert the word into its numerical representation. So in this vocabulary, S to I is going to do this conversion. So it will give us, for a given word given as an ASCII string, it will give us the numerical representation of where that word is in the dictionary. And so if you go and run this for some example, first of all, we are printing what the vocabulary size is. The length of this vocabulary, so this is the vocabulary that we just built here through this process from the training data set, is already pretty large. It has 95,812 different words in it. So that's that. So now that we have this whole dictionary of 95,000 words, if you take some random sentence, as long as all the words from this sentence belong to the dictionary, we can get this vector now, or this list that represents each word in the dictionary from that dictionary. So what this number tells is that the word I is stored in the dictionary at the location of 283. And this word love is stored in the dictionary at this location. The word two is stored in the dictionary at this location, and so on. So effectively, we now have a numerical representation instead of words. So this string now can be encoded in numbers. So any questions about this so far? Does it make sense? Feel free to type in your questions, or feel free to turn on the microphone and ask those questions. So what we have accomplished so far, we were able to take the text and convert it into numbers. And what's nice about this approach, because we have the same dictionaries and pretty much any text, if we convert it into numbers against this dictionary, then we will have the same, the same representation. Word play always will be represented with the same number, and word my will always be represented with the same number, regardless of what this text is, because we built it against the same dictionary. Now, how do we build a neural network that actually can take this information and be able to do something with it? So, for example, recognize what is the purpose of the sentence? What is the class that the sentence belongs to? Does the sentence describe something about the business news or about the world news? So how do we do that? Well, turns out that this representation itself is not quite sufficient to accomplish even that simple task. We need something else. We need another type of representation in which effectively we can somehow characterize which words are used, and then see how this characterization of which words are used is close or far from different classes that we have. And for example, so one simple technique for that is called the bag of words representation. So the idea here that we essentially go and count how many times a given word occurs in a given sentence. And then with this representation, we can then check if the given sentence is closer by the types of words used there to the sentences that typically describe sports news or typically describe world news. The idea here is that typically the same collection of words or the same sort of smaller dictionary is used to talk about one subject, and a different dictionary, the different collection of words is used to talk about a different subject. And so that's the idea of this bag of word representation. So that bag of word representation has to be built against some corpus or some collection of words that are used. So here's a much simpler example. So scikit-learn actually has this feature which enables us to build this bag of words representation. So we'll import it first, and then so what we're going to do, we are going to take this as the corpus. So we will say that we're going to build a very small dictionary that consists of just this collection of words. And then when I have another sentence that has some of these words, I will build a vector which says how many times the word "my" appears there, how many times the word "dog" appears there. But we only actually are going to build this vector to indicate which words from this corpus are present in this sentence. So for example, "my" is not present in this corpus. "Dog" is present once. "Likes" does not exist there. "Hot" exists twice there. So if I go into this work, I will end up with this vector, which I will convert to print array, which looks like this. Effectively, what this vector says that we are going to build bag of words representation for this sentence using this as a corpus, using this as a collection of words. And so what it shows that there is word "dog" that exists once in this, because there is "dog" here, so it is in the corpus, and so this if my sentence has a word "dog," it will appear here as a count 1. So the word "hot" is used twice, so somewhere there the count for "hot" will be set to twice, and so on. So in other words, this transformation gives us the ability to say how many times each individual word appears in our representation relative to this corpus of words, relative to this dictionary, essentially, the dictionary built out of this corpus. Now, this could be immediately used to basically to build a model that will enable us to look, what the sentence is trying to say, what is the purpose of the sentence, or what category the sentence belongs to. Why this is the case? Because if this sentence has, word "dog" used many times, then the count for that word will be high. If it uses "hot" many times, then the count for that word will be high. And so perhaps other sentences that talk about similar subjects, they will have similar counts. They will not count any other words, but they will include words which are part of this representation. And therefore, there will be some similarity. And so we can build a network that looks for the similarities between these bags of words that will enable us to do the classification. So what we're going to do, we're going to build this bag of words representation for our training data set. So let's just do that. So we will basically implement this function, this method that will turn. So given some word, so this is, or given some sentence, this is the sentence from our training data set, the very first sentence there. So given this sentence, we can actually build a histogram of occurrences of all of the words in this sentence. Now this is going to be performing these calculations in the 32-bit floating point representation. So it will be floating point numbers. So you see there is a dot after this. But this vector, so what's the size of this vector? This vector will be as long as the entire dictionary, the size of the entire dictionary. If our dictionary was 92,000 something, then we will, for each of the sentences from our training data set, we will build a vector of that length of 92,000 something more elements in it. And each time, so basically that vector will tell how many times a given word, a word from the sentence appears relative to that dictionary that this bag of words is built against. So now, of course, this is a pretty large vector, right? So perhaps you can immediately see one of the shortcomings of this method, that if you have a large dictionary, then every single sentence will have to be represented with a very, very long vector. And maybe that's, obviously that's not a very efficient representation, because this vector is going to have a lot of zeros in it. Suppose you have a sentence which has, say, 12 words in it, and the dictionary has 92,000 words. That means that 92,000 minus 12 elements in this vector will be set to 0, and in the best case, only 12 of them will be set to 1, to indicate that that particular word is present. But however, nevertheless, it's already a good starting point, because typically sentences which talk about the same subject have a good chance to have some overlap in using the same type of words. Let's just go with this idea that we will build this bag of words classifier for our entire, based on our entire dictionary of words coming from our training set, and then we can build essentially the models that can use this representation to do the classification. So, but first we need, first we need to convert our entire data set. So that basically we have this words represented in bag of words representation. And this actually can be done by using this bonify function that we will write here, that we will pass in our data loader. So data loader is going to give us an iterator of some sort. So this iterator is going to have a training data set as an input. It will produce collection of batches of some size, so far our training data set is just text, right? We haven't done anything to it yet. Well, actually, so it's a text that we need to convert to numerical representation, and then we also need to convert it to the bag of words representation. And so for that we will use this parameter called collate function, which we will supply this code that is a function that performs that collation. So what exactly is happening here? This function essentially, collate function gets a list of batch size tuples, and then it returns a pair of label feature tensors for the whole mini batch. And so that's what this function is going to do. Yeah, so it is, so somebody is asking this question about in the bag of words. So it is not entirely binary. So 0 means the given word is not present. 1 means the word is present once. 2 means it's present, that it is present twice, and so on. So the number that is in this representation, like number 2 here, tells us that some word, some particular word, is present 2 times. Is present 2 times in that sentence. So it is almost like a binary, except that numerical value also tells how many times it is present. Okay, so this, if we run this code, we are going now to create these data loaders, which we can use in our training, for that to create in our model. And so what this is going to do, this is going to pull us a sentence or headline, news headline from the training data set, and is going to turn it into a bag of words against that dictionary built against a dictionary from the training data set. And then having this bag of words representations, we can build a very, very simple model. This will be just literally just a 1-layer model will be a linear layer, very large linear layer. So I guess it will have 92,000 inputs, and this linear layer will just do some recombination, and then because we are trying to we are trying to classify this output into one of 4 categories. We just need something like a log softmax function to sort of figure out some sort of a probability of a given sentence belonging to one of these 4 classes. So this is the model. This is pretty simple model. All we have to do is just to say that we have a linear model of input size of vocabulary size. So that input will be 92,000 and output size of 4. And that will go into log softmax, which will simply give us a probability of belonging to one of these 4 classes. And then what we will do, we will build this standard training loop that you kind of had an example in one of the previous lectures when we talked about how to build models and how to train models with PyTorch. We essentially go through the batches from the data loader, and so we'll use a zero-grad optimizer. We will apply this input, so features, to our network that we just defined it here. We will look at the loss function. So the loss function will be set to cross-entropy function. We will do the backpropagation. The optimizer will do the updates for the weights. We will accumulate our loss. We will look at the prediction, so we can print this prediction, and we can, this extra code here is to occasionally print some output so that we can see there is a progress of some sort in our training. And so we'll do it for some number of epochs. So that number of epochs is going to be a parameter that we will supply when we make a call to this model. So this will be our method, train epoch, and this method, once it's done, is going to have the trained network, but it is also going to print us something about the overall loss and overall accuracy. So a pretty standard process that we have to go through. So if you go and train it, so this takes a bit of time. So we are going to train it for 150 or 1,500 epochs, and we will occasionally print the results of this process. So you will see that it takes some considerable time to go through this training, simply because we have a very large input vectors. These are vectors of the size of the dictionary, and so each word in each sentence in our input from our training data set has to be converted into that vector of 92,000 elements. And so when we start training, we will see that our accuracy after some number of epochs looks like after 3,200 epochs is this. And if we keep training it, we will see that this accuracy will improve a little bit. But we will stop at this level. So we are not going to go beyond that many altogether. Okay. Of course, there is a problem with this approach. The main problem is that, some words actually have, first of all, different meaning depending where they're used. And also, some words are parts of multi-word expressions. So, for example, the word the hot dog consists of 2 words, each of which, if you interpret it by itself, has a very different meaning. But then, on the other hand, if we put them together, the meaning is yet has something else. Has a very different meaning that each of these words taken not considered to be together. And so, if the words hot and dog always are used in the same vectors, it can be confusing to our model, because the model will not be able to know to differentiate between hot used in one place and dog used somewhere later, or hot dog used as a one together to represent something else. The model will not be able to differentiate that. So one technique to deal with this is to try to build, instead of build a dictionary which has only single words in it, also to try to build a dictionary which has what's referred to as an n-gram representation, meaning that we are not only going to consider individual words, we are also going to consider pairs of words, or triplets of words, or quadruplets of words, and so on. And so in our bag of words representation, we will be counting not only occurrence of individual words, but we also will be counting occurrence of pairs of words, and so on. So here's an example going back to this small corpus that we used previously. Basically, if we go and try to build the dictionary, the vocabulary here, our vocabulary is going to have all the individual words. And for this, all of these words, we will have an index where this word appears. But then it also have pairs of words. So there is I and like, there is like and hot, there is hot and dogs, and so on. And so we will also have these pairs of words that will be part of our extended dictionary or our extended vocabulary. And then we can build bag of words against this vocabulary. Taking our original sentence that we built before, if we go and build it against this new vocabulary, we'll have a much longer vector because this is much longer. This dictionary is much longer. But we will count not only individual words, but also occurrence of specific combinations of words. So, for example, we have hot dogs, which is also appearing here. And we will have a count for it set to 1 to indicate that this phrase hot dogs also appears in this sentence. Now, this can help us to differentiate between cases where the sentence talks about something hot and the sentence that talks about something dog. But this representation will let us to consider hot dogs as one item that maybe has a different meaning than from other cases. Of course, this approach requires building a much larger dictionary. And if you, for example, go and build this dictionary for our training data set, and we print the number of words in this dictionary, we will see that from 92,000 words, we actually went to something like 1,300,000 words in this dictionary. So the dictionary exploded significantly. And so if you just want to go and build a bag of words representation against this dictionary, we will end up with very, very large vectors. And so it can be done, and we can try to train our model against this vector, so using these vectors as inputs. But of course, it will be much more time consuming, much more memory consuming, and the results are not going to be any better compared to what we already do, because this representation is very, very sparse. So instead of this sort of representation, this bag of words against this dictionary, we actually will introduce another type of representation. So in the bag of word representation, word occurrences are evenly weighted, meaning that word hot and word dogs, these two words have the same weight, regardless of what they actually are, what they mean. However, it is clear that there are some words which are used much more frequently. So, for example, these words a, in, and so on, they are used very frequently, and yet they don't have any meaning. They are less important for the classification. They are present in every single sentence, but they don't really add meaning to those sentences. And in fact, for a typical NLP task, this will be not the words that will describe what's happening, what's the meaning of the sentence. So we want to ignore these words, or we want to eliminate these words from our classification tasks. So this can reduce the dictionary, and this can reduce the vector sizes that we work with. And so there is one particular representation called term frequency inverse document frequency, IDF, that basically enables us to take this bag of words representation and basically replaces the presence or absence of a given word in that representation with some floating point value, which is related to the frequency of words occurring in the original dictionary or in the corpus against which this is built. So here is sort of the formula that describes how this is computed. So basically, instead of having a binary 0 or actually it's not quite binary, so binary that the word is not there or some number that says how many times this word occurs, we will have this weight for a word I in the document J that define it like this. So here in this formula, so TF sub ij is the number of occurrences of I in J. That is basically a bag of word representation that we used before. But however, this gets modulated by the logarithm of this ratio, where n is the total number of documents in the collection, and df of sub I is the number of documents contained in the word I in the whole collection. And so basically this value, this weight value, increases proportionally to the number of times a word appears in the document, and is offset by the number of documents in the corpus that contain the word. And this helps to adjust the fact that some words appear more frequently than others, and therefore perhaps many of those words are not contained in a specific meaning, and then maybe they can be somehow omitted from the classification. So for example, if the word appears in every document in the collection, then this means that the df of I equals n, and the weight will be 0. So which means that we don't really care about that word, because there is nothing that word can help us to differentiate between the two documents or all the documents. It appears everywhere, so it's not giving us the information that can differentiate between two documents. On the other hand, if one document has a very specific sense and another document has a different set of words, then the weights for those words will be high because they are discriminative enough. They give enough of the difference between the different documents, and we can effectively use them to differentiate between those documents. So again, scikit-learn has the tools necessary for us to build this representation. So we will import this tool, and so for example, for the if we now use this collection of n-gram consisting of 1 and 2 words only from our original corpus. Remember that our corpus was this very small collection of words. So this was our original corpus. If you just build something against this corpus, we will see that this representation now we're going to have different values that indicate how many times each word, the combination of words, appears in the text. Now this is a very small representation, so it's it's hard to see the value of this. But the point here is that now, if there are frequent words that occur across different sentences or different documents, then their weight, their contribution will be 0. So we will not take them into account when we need to do the classification. Only the collection of words which are unique to different documents will appear here as some numerical values. And so so this will help us to get a somewhat better results. However, even this representation is not good enough, because bag of words representation simply looks at the presence or absence of words. It doesn't say anything about the order of these words. And obviously, when we provide a sentence, when we say a sentence in English or in any other language, the order in which words are put together has a very different, results in a very different meaning of what that sentence is providing. So the order of words and the connection of words actually is very contextual, and if we cannot extract that contextual meanings, then this bag of words representation is not really helping us much. So it may be good enough to train this model where we try to classify if text belongs to one category or another, but probably not beyond that. Probably there is very little that can be done with bag of words representation beyond just that very simple classification. We will not be able to extract any good meaning from the sentences if you do not consider the relations between words. Okay, so that's that. So let's actually see what else we can do. So this bag of words representations, even if we sort of come up with this sort of improved representation where we look at the frequencies and all that, even sort of that sort of representations still results in very high dimensional representations, which of the size of the entire vocabulary, and that makes the problem, the classification problem, hard, because we have to have our model, we have to have a lot of memory, and we are using this very sparse representation, which is not really giving us any particularly useful information other than taking a lot of memory. And then, of course, each word is treated independently from each other. That is, there is no sort of connections built between these words. And so to improve this, we need some sort of a different representation that starts to look not only at how to reduce these very large vectors into something more meaningful, but also into how to try to find some relations between the words and actually start to use those relations. So for that, we are going to use a different data set. So we'll use this data set, but there is, so far we'll use the same data set, but there is kind of a different set of tools that we need to promote. There are some torsional P examples that we will need to make available for us. So we are going to, so we will have a loader in this collection of these tools that I just imported. We'll have a loader function, which will load the data set. And so what this loader function is going to give us is the following. It will give us the training data set, obviously, the test data set. It will give us a list of classes, and also will give us the vocabulary. So as before. And so when we run this, we will see that, so it takes a bit of time to load the two data sets, training and testing. It's the same vocabulary, the same 95,000 words in this vocabulary. So we will have that. So, so the idea of embedding is to basically represent words in a lower dimensional format. So we will have this much shorter vectors, but these vectors will be much more dense. And these vectors also somehow reflect some semantic meaning of words, of a given word. So we will talk later about how to build these meaningful embeddings, but for now, let's just think of embeddings as a way to basically just reduce the dimensionality. And so for that, we need to have a special layer in our model that is going to take a word as an input and will produce some sort of an output vector of a given size, and we will specify it as embedding size. So in principle, what this vector is going to do, this layer is going to do, it is going to take a word and just come up with some representation that will be of a much smaller size. Let's not worry about what's the meaning of that representation. Let's just worry about the fact that it will be something of a much smaller size. That can be accomplished by something similar to the linear layer, but instead of taking sort of one hot encoded vector, this layer is going to take a number that represents a word in the original dictionary as input. And so by using this embedding layer as the first layer into our network, we can basically switch from bag of word representation to some sort of an embedding bag model, where we first convert each word in our text into corresponding embedding, and then we compute some average function over all of those embeddings. So our model might look like this. So each of these words that we have in our text, they will be through this embedding layer that they will be represented as some numerical values that will be averaged, and some linear function will be applied to them. And so our classifier network now will start with this embedding layer, and then with some aggregation layer and linear classifier on top. So basically, if you look at the models that we will build, we effectively will build something that will include fully connected layer at the end, and then which will be fed by the embedding layer of some sort. So the network takes embedding at the first layer computes, say, mean value over those embeddings, and then computes and applies, puts this into a fully connected layer that will give us some final result. So this is how this network will look like now. Of course, one of the problems with this approach is that, different sentences or different texts that we want to classify, they are going to have different size. All these mini batches that our data loader is going to return, they will have to be created in a certain way, specifically so that they all have the same number of these representations or embeddings in them. When we built bag of words, we kind of didn't have to deal with this problem because this bag of words was built against the same dictionary, and so every vector for every sentence or every text, every document would have the same length. It would be the length of the dictionary. Regardless of how short or how long the text is. However, when we sort of start to use some embeddings, we would end up with variable number of words in each text sample, right? And because embeddings now is it's not building bag of words representation anymore. It is actually sort of bound by how many words we have in the sentence or in the text. And so all these mini batches will have to have different size. So one simple approach, perhaps not the best approach, but one simple approach to apply here is to simply apply some padding. So if you have a very short sentence, we can apply a padding to make the embedding of the same size as the embedding for the longest sentence or the longest text that you have to work with. And again, this can be done through the collate function in the data loader. We just need to we will implement this padding function that is going to also to extend an embedding representation to be of the same size for all the samples that we work with. So our data loader is going to take this collate function as padding, again with the same batch size of 16 and so on. But here we will guarantee that each vector will be of some fixed size. And if that vector if the sentence happens to be shorter, then that vector will be zero padded to give us the same size for all of the data sets, for all of the samples that we have to process. So having this, we actually can build our classifier. We essentially can train the model using this training function we have defined it in the previous example, in the previous notebook. Our network will be this embedded classifier, which we'll just build here. So that's this class, and we will just run it for a few epochs. So at this point, we also may want to try to use some sort of accelerator for this, because this is going to take some considerable amount of time to train on the CPU, because those embeddings also will take time to be built. So we see that our network starts with some lower accuracy, but eventually this accuracy improves, and the overall loss sort of improves over time as well. So we only train it here for 25,000 records, but we can kind of extend that to train longer. And if you play long enough with this, you can get apparently accuracy up to 90%. So that's not a bad approach. So the drawback of this approach, though, is that you have to zero pad. And essentially, for one longer sentence, you can have something meaningful, and there will be meaningful values in this embedding vector. On the other hand, for shorter sentences or shorter text, you will have a lot of zeros, which do not contribute to the classification. In fact, they can be misleading to the model. So what would be nice now is to replace this sort of very fixed length vectors with some sort of variable length representation. We just need to somehow modify our model to keep track of how long is this vector for a given sample. So So what we would like to do is to basically build a model that will accept an input in which we will basically provide these sequences stored as a one large vector that tells where the next embedding begins. And so that the model doesn't have to have the zero padding, and zero padding can be done internally if it is needed. So we are not solving the problem of zero padding or the impact of zero padding. We are just solving the problem of storage. We no longer need to store a zero padded vectors that will be generated on the fly by the model, but what we store before the representations that we store before sending it to the model is not going to have that zero padding. And so that tool is also available in PyTorch, and to work with this offset representations, we'll use embedding bag layer. This embedding bag layer is similar to what we've done previously, except that it takes this embedding bag as an input and will generate internally the zero padded layer, this zero padded embedding. So this will be a model that we will implement. So our input into this model will be, or our first layer will be embedding bag. This embedded bag will need to know something about the entire dictionary and the dimension of our embedding, but then it will internally create zero padded representations. Then we will use the linear function as before. So that's the model. We can, of course, now we need to generate the data set in a slightly different way. So instead of generating a data set that consists of zero padded vectors or embeddings, we'll generate a data set that is kind of compact, and we just know where each of the samples begin, and then we can supply this data to our input layer that already knows how to work with this data structure. So for that, we will develop a different function, different collate function that will perform exactly that at work. That collate function is going to basically keep track of, it is going to generate the data set in that particular format. So we can then modify our classifier. So effectively, so now our network needs to accept sort of different set of parameters, the data vector and also the offset vector. So the data vector will have all of the embeddings, and the offset vector will tell us where an embedding for a specific sentence or a specific document is located. And these data vectors are of different size. So the data vector will contain the entire data set, but with all of the embeddings, but the offset vector will tell us where the embedding for each specific example is located, or for each specific sample is located. And which means that we have to modify our data loader accordingly. And so the training function will be modified slightly to sort of implement these changes. But again, so we can, the approach for training will be the same. It's just we are basically building a different interface to this training model. So if you run it, then we will see that again, we are going to see more or less the same performance as before, because we haven't really changed anything the way the data is embedded. What we have changed is basically the amount of memory that we need to keep track of our data set, and the way this data set is represented. So so in this examples that we look at so far, the model embedding layer basically somehow figures out how to map words from vector representation. However, this representation still doesn't have any sort of semantical meaning. So our model is trained to take a bunch of words and somehow combine them into some embedding, but there is no semantical meaning to that yet. that semantical meaning is not something that this sort of embedding layer can provide us with. Of course, semantical meaning is something that is very important. For example, that similar words or synonyms would correspond to basically the same things. If I say big and large, these two words roughly mean the same thing. So if I don't include semantical meaning in my representations, then effectively embedding for the same sentence in which one word is replaced with word big, and in another instance it's replaced with word large, actually will be different, but they should not be, because in principle they mean the same. So it would be nice to sort of minimize the distance between these embeddings if there are synonyms or similar words used in place of each other. So, to get something like that is not that trivial, because we would need to, first of all, have a data set, which kind of a dictionary that specifies, all the synonyms and all the similar words. And we need to pre-train our embedded model in a very specific way. In such a way that we kind of, have these correspondences, and these correspondences are known and taken into the account by the model. And so one of the first ways to train semantic embeddings is called word-to-vector method. It is based on two main architectures that are used to produce a distributed representation of words. So first of all, we use continuous bag of words representation. In this architecture, we train the model to predict a word from surrounding context. So basically, if we are given some sequence of words, we want to predict what this word in the middle of the sequence might be, based on the words before and words after. So the goal of this model is to predict this word in the middle based on what we saw before and what comes next. So that's one representation. And then continuous skip-gram is kind of the opposite to this. The model uses surrounding window of context words to predict the current word. And so one of these representations, of course, is faster and the other one is slower, but it does a better job of representing infrequent words. So there is sort of a picture here that explains what is it that we are trying to do. So in one example, or in one instance, for this so for this continuous bag of words representation, we are given few words before and after, and we want to predict the current word. And in other representation, we are given a word, and we are trying to predict what might follow, or what might be before that word. So actually, for this tutorial, to work with this example, this representation, this tutorial actually uses a different model, a pre-trained Google News data set, which is part of this library. And so we can just go and load this. Where is my cursor? So we can just go and load this model. It is going to take a bit of time, because this is a pretty large model to download compared to that model that we just saw. But while it's downloading, we actually can try to take a look at some of the examples of what's in that model. So for example, if I can ask questions from this model, give me all the words which are similar to word neural, and it is going to go and generate a sequence of words. So neuronal, neurons, neural circuits, neuron, cortical, brain circuitry, and so on. All of these words have some similarity to the word neural, and they all will appear in this list of similar words. So this pre-trained model now can give me this weight of how close a given word is from how close synonyms or similar words are from a given word. So this model starts to have semantical relations between different words. So of course we can also extract vector embeddings from the word to be used in training or classification model. And so here's an example for the word play, for example. So for that, this will be the numerical representation for this word play. That's sort of the vector embedding of this word from this classification model from Google News model. So so I guess one interesting thing about this representation that it is actually possible to manipulate these vector representations to change the semantics. So for example, we can ask questions like find words whose vector representations are very similar, very close to a given few words. So the example that is given here, so we look at what would be the word that is similar to describing, it has the same meaning as kin, woman, but doesn't include word man in it. So we will look for a word, for the word that has this meaning of the woman kin and doesn't include the word man in it. So that there is a negative weight given to the word man. And sure enough, it's a queen who has this sort of meaning. So in fact, we can, with this representation now, we can actually do some very interesting inferences where we can find semantically similar words, not only given by a specific word or combinations of words, but also excluding some other permutations, some other words. So these two representations basically are predictive embeddings. Effectively, what we've done here, we're able to predict what would be a word that has these characteristics of being similar to kin, woman, but not similar to man, would not include word man in it. So that's a predictive embedding. And with this predictive embedding, of course, they have this disadvantage that it can also take the local context into the account. There is no global context that is embedded in this representation, and this is one of the sort of shortcomings of word-to-vector representations. There is a different representation called fast text, which builds on word-to-vec representation by learning vector representations for each word, and then the character engrams found within each word. So the values of these representations are then averaged into essentially one vector at each training step. And so while this adds a lot of additional computation, because we have to do this a lot of pre-processing and pre-training, it actually enables word embeddings to encode sub-word information. There is another technique called GLOW-V that leverages the idea of co-occurrence matrix. So this sort of co-occurrence matrix can be more expressive and can find sort of not obvious non-linear word vectors that sort of connect words together. So let's actually just look at one more example of using the pre-trained embeddings in PyTorch using embeddings similar to what's done in the word-to-vector. Of course, so we need to take into account that vocabularies of pre-trained embedding and our text corpus will likely not to match. So therefore, we will initiate weights for the missing words with some random values at first, and then we'll have to do something about those not matching things. So first of all, what is the size of this embedding? So for example, in the word-to-vector embedding for the word hello, we will have an embedding of size 300. If we sort of try to populate the matrix with this words that have some subcomponents similar to hello, we will actually end up with pretty large number of words. So the other thing is actually, so what this code does, this code also tries to take this Google Net data set and checks how many words are in our original dictionary. And so we will see that there is an overlap between the dictionaries used in our original data sets that we used and the data set in the Google map, but there is a Google Words data set, but there is also large discrepancies. There is a lot of words which are missing there. So, but anyway, so we will try to use this representation and try to train our model with this representation, and we will kind of use the same models as before, but we will see that it actually takes a significantly longer amount of time to do this sort of training. What's more important is that we are not going to see a huge increase in the accuracy, which is probably due to the difference in vocabularies. So the vocabulary against which we are doing this training is not the same as the vocabulary of words which we are using. So there is some mismatch between these vocabularies, and there are many words in our training data sets that are not in the original vocabulary. So they are ignored. There is no meaning given to them. So we are not going to see good improvements. But this can be solved, for example, by retraining word-to-vec model on our vocabulary, or loading the data set with the vocabulary from the pre-trained model, so that we actually do not have this discrepancy. So we can actually try this approach. Again, Torch Text has the framework which has a built-in support for this sort of embeddings. And so we can, for example, try to go with GloVe-based vocabulary. So this will read us the GloVe vocabulary. So it takes a bit of time to read it. But then we can actually take this vocabulary and run our data set against this vocabulary, and so we will see that there is a better overall representation for this. So the vocabulary, so we've been using this vocabulary for already. This is the second time that we use it. We first built vocabulary from the words from that AG News data set. And now we are building this vocabulary for GloVe. Vocabularies in generally, this vocabulary in general has some functions that we can use. So one of them is converting text to index, or the other way around. Also getting the embeddings. So we can, for example, take some word from the vocabulary. We can convert it to, that gives us a string that we can get the word from that vocabulary, and we can build the embedding vector to see how it looks like. So here's an example of, for example, so when we try to build this, find this word which is semantically similar to hin and man, but doesn't have the word man in it. And when we search for an item from our vocabulary that has that semantical meaning, we will get the queen as a result. So that that seems to be what we would expect. So if you want to train a classifier with this embedding, we of course have to have the different encoding for our data set using the GloVe vocabulary. So that this function that we have to build here will perform this sort of encoding using that new vocabulary that just loaded. And so we will build this encoding first, and then so we can try to run our model against it. And so this is this training component. So again, so this training is taking some time, and but actually turns out that we are also not getting a particularly more improved model. So one of the reasons why we are not seeing a significant improvement in the accuracy is due to the fact that some words from our data set are still missing in the pre-trained GloVe vocabulary. Even though we tried to remap our data set which we're trying to classify into this GloVe dictionary, there is still some mismatch between the words used. Okay, and of course we can come up with our own embeddings. So far we've been sort of using pre-trained semantic embeddings, but this embeddings can actually build for specific tasks and for specific domains, and we perhaps can get a much better results because we will kind of build a model which will give a particular weight to the embeddings for specific purposes, built for specific purposes. I think this is, so I think I'm kind of starting to run out of time for this tutorial. There is a bit more with recurrent networks. So the problems that we are running so far is the following. We can kind of look at individual words. We can look at collections of these words, but this does not necessarily give us it does not necessarily enable us to answer something about the meaning of sentences. We can only classify sentences or text into some categories based on the presence or absence of specific words. But we cannot answer questions like, so what is this sentiment of the sentence? Or can we extract some name and entity from the sentence? So these techniques and these representations are not going to help us to answer this sort of questions. So to be able to answer that sort of questions, we kind of need to start to build up some history of what we see. We should not look at each individual words or n-grams of words. We should start to see the sequences in which these words appear. And so the techniques which are used for that are based on some recurrent neural networks, where we will essentially have this recurrence model in which we will look at the input and also at what this model saw previously. And we will produce this new representation that takes into account not only the new word that we are given the sequence access to, but also at what sequence of words we have seen previously. And so that's sort of this recurrent neural network set that can enable us to answer that sets, the more complex, more challenging questions, such as finding name and entity, or such as trying to extract some useful summary of the text. So that's kind of I guess that's kind of outside of the time that I wanted for this tutorial. So perhaps maybe we can have another tutorial where we'll talk about this recurrent neural network models. But so I'm done for now. So if you have any questions, please let me know. And that's all for today's tutorial.